To determine the supply wire size, we need to calculate the current in amps required by the welder. The formula for calculating current is current in amps equals power in kV amps divided by voltage. In this case, current equals 43 kV amps divided by 480 volts equals 89.6 amps. Using a table of wire gauges and ampacities, we find that a number 2 American wire gauge wire can handle 95 amps, which is the closest size above our calculated current. The appropriate fusing depends on the National Electrical Code requirements for the specific installation. Typically, a fuse rated at 125% of the calculated current is recommended. Fuse rating equals current times 1.25 equals 89.6 amps times 1.25 equals 112 amps. Therefore, a 110 amp fuse would be suitable. The formula for calculating wire size for transformers is wire size in American wire gauge equals 10 plus the log of current divided by 1.724 divided by the log of 2, where current is a calculated current in amps and 1.724 is a constant. The fuse selection needs to adhere to the National Electric Code. Section 450.3 addresses transformer overcurrent protection. Primary side protection for transformers rated over 600 volts requires an overcurrent device rated not more than 125% of the rated primary current, where the transformer has a coordinated thermal overload protection. For transformers rated 600 volts or less, the overcurrent device should be rated not more than 125% of the rated primary current. However, if the primary current is less than 9 amps, a maximum rating of 167% is allowed. If the primary current is less than 2 amps, up to 300% is permitted. The secondary side protection depends on the number of primary overcurrent devices. If there is only a single overcurrent device on the primary side, the secondary overcurrent device must not exceed 125% of the rated secondary current. If there are primary and secondary overcurrent devices, the secondary device can also be rated up to 125% of the rated secondary current. For supervised industrial installations with specific conditions, different rules apply. The primary side overcurrent device can be set up to 250% of the transformer's rated primary current, and the secondary overcurrent device can be set up to 125% of the transformer's rated secondary current. The conductor ampacity for the primary and secondary conductors is covered in section 450.4. Primary conductors must have an ampacity of at least 125% of the transformer's rated primary current. Secondary conductors must have an ampacity such that the overcurrent protection device protects according to its ampacity. For a single-phase transformer, the rated primary current is calculated by dividing the transformer's volt-amp rating by the primary voltage. Similarly, the rated secondary current is calculated by dividing the volt-amp rating by the secondary voltage. For example, if a 43 kV transformer has a 480 volt primary and a 240 volt secondary, the primary current is 43,000 volt amps divided by 480 volts, which equals 89.6 amps. The secondary current is 43,000 volt amps divided by 240 volts, which equals 179.2 amps. Using the 125% rule, the primary conductors must be rated for at least 112 amps, and the secondary conductors must be rated for at least 224 amps. The overcurrent device on the primary side should not exceed 112 amps, and the overcurrent device on the secondary side should not exceed 224 amps. For the wire size calculation formula, the American wire gauge, often abbreviated as American wire gauge or AWG, is a standardized wire gauge system used predominantly in the United States for the diameters of round, solid, non-ferrous, electrically conducting wire. The larger the American wire gauge number, the smaller the wire. This is counterintuitive. A number 24 American wire gauge wire is smaller than a number 12 American wire gauge wire. The American wire gauge standard is used to determine the current carrying capacity of a wire. This is based on the cross-sectional area of the wire. The formula to calculate the American wire gauge of a wire given its diameter in inches is American wire gauge equals -39 times the diameter in inches plus 36. Alternatively, if you know the diameter in millimeters, the formula is American wire gauge equals -39 times the diameter in millimeters plus 31.4. When selecting the appropriate wire size, it is important to consider the National Electric Code, or NEC, requirements. The National Electric Code specifies the allowable ampacities for various wire sizes and insulation types under different conditions. The ampacity of a conductor is the maximum current in amps that the conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors affect the ampacity of a conductor. Firstly, the material of the conductor. Copper and aluminum are the most common materials. Copper has a higher ampacity than aluminum for the same wire size. Secondly, the size of the conductor, which is generally indicated by its American wire gauge. Larger conductors have higher ampacities. Thirdly, the insulation type. Different insulation materials are rated for different maximum operating temperatures. Common insulation types include THHN, THW, and XHHW, each with different temperature ratings and suitable applications. Fourthly, the ambient temperature. Higher ambient temperatures reduce the ampacity of a conductor. Correction factors are applied to adjust the ampacity for ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. Fifthly, the number of conductors in a raceway or cable. When multiple current-carrying conductors are bundled together in a raceway, cable, or conduit, their ampacity must be derated to account for the increased heat generated. The National Electric Code provides tables for ampacity correction and derating factors based on these conditions. The National Electric Code Table 310.15b16 provides adjustment factors for ambient temperature. For example, for a THHN conductor with an ampacity of 30 amps at 30 degrees Celsius, if the ambient temperature is 40 degrees Celsius, the adjustment factor might be 0.91, resulting in an adjusted ampacity of 27.3 amps. The National Electric Code Table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. For example, if there are 4 to 6 current-carrying conductors, the ampacity must be derated to 80% of its original value. If the conductor originally had an ampacity of 30 amps, the derated ampacity would be 24 amps. The National Electric Code also covers conductor installation requirements. Conductors must be protected from physical damage. This might require using conduit or other protective measures. Conductors must be properly supported and secured. Conductors must be identified and labeled correctly. Connections must be made using approved methods and connectors. Overcurrent protection devices, such as fuses and circuit breakers, are crucial for protecting conductors from overloads and short circuits. The overcurrent protection device should be sized to protect the conductor according to its ampacity. However, the National Electric Code provides specific rules for sizing overcurrent protection devices, particularly in motor circuits and transformer circuits. For motor circuits, the overcurrent protection device is often sized higher than the conductor ampacity to allow for the motors in rush current during startup. For transformer circuits, the primary and secondary overcurrent protection must be sized according to the transformer's voltage and kV amps rating. The National Electric Code also has specific requirements for grounding and bonding. Grounding ensures that non-current carrying metal parts of an electrical system are connected to the earth, providing a path for fault current to flow back to the source. Bonding ensures that all metal parts of an electrical system are electrically connected, creating a low impedance path for fault current. Grounding and bonding are essential for safety, helping to prevent electrical shock hazards. The National Electric Code Section 250 covers grounding and bonding requirements in detail. The equipment grounding conductor must be sized according to the size of the overcurrent protection device in the circuit. The grounding electrode conductor connects the grounding system to a grounding electrode, such as a ground rod or water pipe. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. In summary, selecting the correct wire size requires calculating the current, considering the conductor material, insulation type, ambient temperature, number of conductors in a raceway, and following the National Electric Code requirements. Proper installation, including protection from physical damage, support, identification, and proper connections, is also crucial for ensuring a safe and reliable electrical system. Overcurrent protection, grounding, and bonding are essential safety measures. Always consult the latest edition of the National Electric Code and a qualified electrician for specific applications and installations. For example, let's consider a scenario where you need to install a 20 amp circuit to supply power to a series of lights in a commercial building. The circuit will run through a conduit with 6 current-carrying conductors. The ambient temperature is expected to reach 40 degrees Celsius. Firstly, determine the minimum wire size. Since the circuit is rated for 20 amps, you might initially think that number 14 American wire gauge wire is sufficient, as it has an ampacity of 20 amps under certain conditions. However, you must account for the derating factors due to the ambient temperature and the number of conductors in the conduit. Secondly, apply the temperature correction factor. Assuming you are using THHN conductors, the ampacity is based on a temperature rating of 90 degrees Celsius. According to the National Electric Code Table 310.15b16, the correction factor for an ambient temperature of 40 degrees Celsius is 0.91. Apply the derating factor for the number of conductors. With 6 current-carrying conductors in the conduit, the ampacity must be derated to 80% of its original value, according to the National Electric Code Table 310.15b3a. Fourthly, calculate the adjusted ampacity. Start with the ampacity of the number 14 American wire gauge wire, which is 20 amps. Apply the temperature correction factor of 0.91, resulting in 18.2 amps. Then apply the derating factor of 0.8 for the number of conductors, resulting in 14.56 amps. Since the adjusted ampacity of the number 14 American wire gauge wire is only 14.56 amps, it is not sufficient for a 20 amp circuit. You need to select a larger wire size. Fifthly, select a larger wire size. Try number 12 American wire gauge wire, which has an ampacity of 25 amps under certain conditions. Apply the temperature correction factor of 0.91, resulting in 22.75 amps. Then apply the derating factor of 0.8 for the number of conductors, resulting in 18.2 amps. The adjusted ampacity of the number 12 American wire gauge wire is still not sufficient for a 20 amp circuit. Try number 10 American wire gauge wire, which has an ampacity of 30 amps under certain conditions. Apply the temperature correction factor of 0.91, resulting in 27.3 amps. Then apply the derating factor of 0.8 for the number of conductors, resulting in 21.84 amps. The adjusted ampacity of the number 10 American wire gauge wire is 21.84 amps, which is sufficient for a 20 amp circuit. Therefore, you should use number 10 American wire gauge THHN wire for the 20 amp circuit in this scenario. Sixthly, select the appropriate overcurrent protection device. The overcurrent protection device should be sized to protect the conductor according to its ampacity, but it should not exceed the circuit's rating. In this case, a 20 amp circuit breaker would be appropriate. Finally, ensure proper installation. Make sure to follow the National Electric Code requirements for installing the conductors in the conduit, making proper connections, and grounding the circuit. By following these steps, you can ensure that the 20 amp circuit is installed safely and correctly, providing reliable power to the lights in the commercial building. Remember to always consult the latest edition of the National Electric Code and a qualified electrician for specific applications and installations.